Okay guys, we're starting. So 4.1 is about extreme values, and one thing we're going to do a lot in this chapter, you start seeing more practical applications with a derivative, like you start seeing why we're doing all this stuff. Eventually you can get to this point where if you're graphing like y equals negative 4x to the fourth power plus 5x cubed minus 2, you'll be able to do this graph more accurately, because what you can do is you can take the derivative, right? And when you set the derivative equal to 0, that represents what kind of tangent line? Horizontal, right? And where horizontal tangent lines happen in the curve? At the peaks and the troughs, right? The tops and bottoms. These are what we call extreme values. High points and low points. So that's what this section is about. And then we'll start graphing later in chapter 4. So you can start seeing a little bit more practical applications for this. The first thing I want to talk about are absolute, maximum and absolute minimum. My favorite word. Absolute. So anyway. So absolute means that just the highest y value in the graph. The highest possible y value in your specified domain. Absolute minimum will be the lowest, also in your specified domain. There's also another thing called local, maximum local minimum. We'll get to that point when the time comes. But for now, we're just looking for the highest possible value for y in your specified domain. The more formal definition states the following. So if you have domain D, f of a would be the absolute maximum if all y values are less than f of a. So this means all y values less than or equal to f of a. So say, for example, a were like, I don't know, 1 here. Say the graph looked like this. Then that would be the absolute maximum, right? If the graph had like n behavior with both arrows pointing down, there's no other y values higher than y value. Whereas absolute minimum, you have something like a parabola. That's a great example. That'd be absolute minimum, right? Because is any y value less than it? Maybe equal to it if you're at the vertex, but so. Because you could have this. That's what's kind of local. So say we have something like this here. If we're talking about all real numbers for this one, there is no absolute maximum because it goes on forever, right? But this right here, we call the local maximum. Because the tangent line is horizontal, so you take the derivative, and for a brief moment, it does seem like a high point. Or for certain domains, this can be a high point. This right here would be an absolute min, because there's no min. Keep those in that forever, right? But this would be called local min. So we'll get to that eventually. All right, so let's do some simple ones. Let's look at y equals x squared. And actually, do you have the dashed curves on yours too? Is it dashed? It's not? Okay, well, it's dashed on mine. Well, I'll trace it so that you see how it's supposed to look. If your domain's all real numbers, right? Oh, that's great. That's Microsoft Word just being too smart for its own good. Okay, I'll just draw with my mouse. There we go. Oh, come on, really? It's frustrating. Okay, I'll just draw it right here. We don't need to use So that's with a domain all real numbers, right? Is there an absolute maximum? No. None. Is there an absolute minimum? At what y value? 0. Always state the y value. When it asks for the absolute minimum, absolute maximum, state the y value. They'll ask for the x value if they want it. But what's the lowest value? It's just 0. Okay. Now let's say you want to graph it from 0 to 2. So you start at 0. And what's the y value when you plug in 2 for the function? For y equals x squared? 4, right? So we'll stop right here. And I just connect them. Right? So it looks just like that. What would be the absolute maximum here for that specified domain? What's the highest y value for that graph? 4. And what's the lowest y value? 0, right? Mm-hmm. Now you can see a slight difference. What's the difference between the second and third graph going to be? So what do we put at 0? Yeah, put a hole. Here we have 4. Connect. Now what is the absolute max? Still going to be 4. But do we have an absolute min? No, I mean, it gets very close to 0. Like you could say 0.0000000000000. I could keep going, right? 1. So we say none. There's no absolute min. Just kind of want you guys to see that difference there. And for the next one, you have holes at both, right? So there are no absolute maximums. So what needs to be true about the interval for both absolute max and absolute min? So if you want both, an absolute max and an absolute min to occur, what has to be true about the interval? Period domain. Or closed, right. Everything has to be included, or closed interval. Nothing could be open. See, the first one was open on both sides, right? But, you know, if you have domain all real numbers, there's a chance you can have one or the other, right? But for the third and fourth, you know, we didn't have both absolute max or min. Only for the second one we did. What else do you think needs to be true? No. Well, it'll probably make more sense when we get to the next example, but it needs to be continuous. Did you say continuous? Oh, I'm sorry. I thought you said something else. I thought you said, yeah, I thought you said inverse or something. Sorry. Sorry about that. Yeah, continuous, right. Like this one here is not continuous, right? So in this case we have no absolute max. Now we could have done this. When I think about it, we could have done that, but if it's not continuous, there's a good chance it may not have an absolute max. Continuity guarantees that you'll have an absolute max. That's kind of what the key thing here is. So that brings me to the next thing here, the extreme value theorem. If f is continuous on a closed interval, and your interval you define as a and b, those are two x values for your specified domain, it will have both maximum and minimum. And these are, again, actually absolute maximum, absolute minimum. So now this is what I was getting to, what the question Claire was asking about a few minutes ago, like how can you tell if it's absolute or why do you call it absolute? Because sometimes you can have local, like here. That would be local max or local minimum. So when it's higher than some of the ones in its neighborhood, that's what I call local. So local max has a y value higher than the ones that are nearby, or local min smaller than the ones nearby. It looks like Liz Blanford can use a grammar lesson. It should be then, not then. So anyway, this is a typo. All right. So in this case, we're going to label the points as absolute or local max or min. So it's actually, because your domain's from A to B, that's going to be our domain. And there's actually going to be five points we're going to locate. So A, B, C, D, and E. And we're going to label each of these. Starting with A. What would you call A? First of all, is it a high point or a low point? It's a low point. Because it's clearly when you move past A, it's start getting higher, right? Is it the lowest possible point in our domain? Yes, it is. So that's an absolute min. Okay, how about B? Because B is at the end of the interval. Is that a min or a max? It's a high point or low point at B. Low point, but it's not the lowest one, right? So we call it local. Basically, what you do is look at what's happening to the left or to the right of the point. Now, because it starts at A, there's nothing to the left, so we only look at the right. And all the points to the right of it start increasing, right? If you look at B, B is the last point, so you can't look at the right. You'll only look at the left of B. And the points to the left of B, the y values are higher. Of course, they do get lower eventually, but for that time being, it is a low point. Okay, what about C? What would you call C? It's local, because it's not the highest one. But it is a max. And how about D? That's absolutely the highest one. And once we start doing this analytically, like once we start taking like derivatives and stuff like that, it'll make more sense why they're max or mins. And E would be local min. E is a bottoming out point, so that'll be a local min. So this definition is a little confusing, but f of c is a local max because in some interval, there's a time when f of c is the highest y value. Like from a to e, for example. If I define the interval from a to e, is f of c the highest y point? It is, right? But if I went from a to b, is the highest y point? No. So, but you could define an interval where it becomes the highest y value. Same with f of d. Actually, oops, that's a typo. That should be f of e. Wow. We should have saw that one. Fe is a local min. Because you could define some interval where, say for example, from C to D, that will be the lowest y value for that time being. And also, there's another thing called half-open intervals. Like, for example, at f of b here, you can say your interval from like D to B, for example. You can say that. Because f of b would be the lowest point. Let's look at the example 3 here, and then I think we're close to being done. Find the extreme values and where they occur. Okay. So what do you guys think for example A? It's a little tricky. For part A, so first of all, you have no extreme value here. Because you don't know how low it can go. I mean, it gets very close to 1 at that point. And over here, same thing. For what reason? Not continuous, right? This was a little bit tricky. But we could say we have a local, you can actually call it a local max. No, at that point, because it's a max because this is higher than these y values. Of course, once you get to this point, that point, then no longer is. But for a specified domain, this could be the highest point. Yeah, go next. Exactly, right. Right, just for a local region. Local max of -2 at x equals 0. This right here will be a local min. That point right there. And that's local min of 2 at x equals 4. So I won't have time to finish B. So we'll do that tomorrow. Yeah, we should be able to finish 4-1 by Wednesday. Sorry, by tomorrow. All right, so we're all set. So homework I'll just put on our agenda. It won't be much. Okay, so we're all set.